Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A level Chemistry Unit 5, Section B for October 2021. I already did a video for Section A and the video for Section C, so both videos will be linked in the description box of this video. So please do not forget to look them up and try to help yourself understand how to calculate, to basically answer some of these questions. I will go straight to the first question. It says, question 18, a series of reactions with iron and iron complexes was carried out. So there are three reactions, we can see 1, 2, and 3. So the first reaction says, a sample of iron was heated with hydrochloric acid and a pale green hydrated salt A with molar mass 198.8 gram per mole was crystallized from the solution. Now when we see here, we can see this is a solid heated with hydrochloric acid. Of course, we're going to produce a solid chloride. And then, because they've told us it's pale green, it tells us this is going to be iron 2, and it's hydrated, so it should be iron 2, XH2O, but here it should be 4 moles of water crystallization. And then we can add up and see if it makes 198.8 gram per mole, the molar mass of this whole thing here. So we go to the second reaction, says, the salt A, that is the hydrated salt, was dissolved in water, forming a pale green solution containing complex B. Now, they've told us a pale green solution. We would expect this pale green solution contains iron 2 ions. And then, so it contains a complex. These iron 2 ions interact with water ligands, forming a complex like this. This is hexaaqua iron 2 plus. We can see here, that is the complex B. And then they go on addition of excess aqueous potassium cyanide, because they have said excess, we suspect this could be a ligand substitution reaction. So excess aqueous potassium cyanide, the solution turns yellow due to the formation of complex iron C. So that complex iron C is because the water ligands have been substituted by Cn minus ligands, as we can see here. That is what we could see. And then reaction 3 says chlorine gas is bubbled through the solution containing the complex iron C. That is the complex iron with the 6 Cn minus ligands. Then a red solution of complex D is formed. This red is due to oxidation. So basically, there is going to be an increase in oxidation state from iron 2 to iron 3. So we're going to form a complex of iron 3. Then there's a salt E. The potassium salt of complex D was then crystallized from the solution. So we're going to decode everything step by step. They said deduce the formula of the hydrated salt A. You must show you're working clearly. So what I said, A contains FeCl2, which is the pale green solution from above there. And then using the molar mass of water, you guys know to find the molar mass of water, if we have 198.8 minus this part here, remember iron is 55.8 and 2 chlorines, 2 times 35.5, this will give us the mass of the iron chloride. Leaving, when we subtract that from the total molar mass, we get this. The part that is left, it means we just have to divide by water. So basically, this is the same as XH2O. If you expected or suspected the salt to be that. So XH2O is that. To find the value of X, since we know this is 18, it will be 18X is equal to 72. And then X will equal to, basically here we can see 4. So this value here should be 4 to make the answer right. So I said A is that. Then they say give the formula of complex B. Of course, this is easy. If this is dissolved in water, we expect the water ligands to come and attach to the metal ion, forming this complex here. This is hexaaqua iron 2 plus. I will go to the next part of this question. C says, complex iron C has 6 cyanide ligands. Draw the structure of C clearly showing its 3-dimensional shape. If it has 6 ligands, of course, they're going to be it's going to be an octahedral shape. Octahedral meaning we have, of course, 6 ligands around the whole complex. In this case, since they are all unidentate ligand or monodentate ligands, they have to be 6 ligands around. Or you would say it's octahedral because it has coordination number 6. So we can see this is one CN, another CN, another one, another one, another one, and the last one. One thing you have to know is the carbon should be directly attached, as we can see here. And since they say they want a 3-dimensional shape, it means you have to show the lines, the wedges, and the dots. If you do not draw it like this, showing the wedges like this, the way I drew them, like this one here, the examiner may not award you marks. So this is showing you the wage, meaning it is in your basically you can see the bonds in your direction. This is in plane with you, and the others are moving into the paper or away from you to the other side. So that is how you can see all this. And then you have to put the charge. Since we have iron 2+, and the 6 ligands of it's going to be total 6 minus. So 2 plus and minus leaves -4 as the balance. That's why we put it up there. So I will go to the next question. It says the percentage composition by mass of salt E is. So here we have the different percentages for potassium, for iron, for carbon, and for nitrogen. So they say calculate the empirical formula of E. What we need to do here is position all the atoms given: potassium, iron, carbon, and nitrogen. Then you get their percentages. Here we have 35.6, 17.0, 21.9, and 25.5. We find you do not have to put the atomic mass if you want, but if you're trying to save time, just go straight to finding the number of moles. So find number of moles should be 35.6 over 39.5.1, and so on. We need to divide the percentage by mass. You divide it by the atomic mass of each of the elements you're working with. Actually, all these, each of the atoms you're working with. And then in the end, I found the number of moles of each as here. Then we will divide through by the smallest number of moles, which is this. That divide by that gives us 1. This divide by that gives us 3. And that divide by that gives us 6. While that divide by that gives us 6. So in the end, we have potassium 3, iron 1, carbon 6, and nitrogen 6. So if you summarize it, you could write it like that or write it like that. They are both acceptable. So this is salt E. I will continue to the next part of this question. It says, write the ionic equation for the reaction of complex ion C with chlorine to form complex ion D. Remember, complex ion C, we have established that it's going to be this without the 2. Ignore these 2 first. I put that 2 to balance the equation. So we have these 2, the FeCN6, 4 minus outside. However, when you react it with chlorine, and again to take you back, I want you to read at what they said. Just a minute. They say chlorine gas was bubbled through solution, the solution containing complex C. Chlorine gas is going to react by gaining the electrons to become chloride. So that means if you have Cl2, there are 2 chlorines, each is going to become chloride. It's going to be twice of them. Meaning we need to gain 2 electrons in this case. And since 2 electrons are being gained, they have to be lost from somewhere. It means this is going to decrease from oxidation state 4 minus to oxidation state 3 minus. From the charge 4 minus to charge 3 minus. Again, let me repeat, this is going to be iron 2 plus, and this is iron 3 plus. Oxidation state 2 plus to 3 minus, overall charge 4 minus to 3 minus. So if it's changing from this to that, it means each is going to be losing 1 electron. So we need to be able to make twice because we need 2 electrons to be gained by chlorine. So we multiply by 2 here to balance the number of electrons that are required to be able to make the equation a full redox reaction. So here, that's why I'm applied by 2 here, by 2 here, to make sure that the electrons that have to be received by chlorine are exactly 2. So in that case, the oxidation state changes from 2 plus to 3 plus, or the overall charge changes from 4 minus to 3 minus. So let's see lastly, they say complete the table using the tick as appropriate to identify the type of each reaction. So they said neutralization. Of course, there was no neutralization reaction. There was no acid-base reaction, actually, or neutralization. There was a ligand substitution reaction, and that was reaction 2. Let me take you back as well to see reaction 2, what it was all about. In reaction 2, we saw, ligand substitution because the Cn minus kicked out, basically, the water ligands. The water ligands were substituted by the Cn minus. Okay, that is correct. Let's go back. That is correct. And then the redox reaction, which is this one here, we have just seen whereby the chlorine is gaining 2 electrons, and then those electrons had to be donated by the complex that was there previously. This brings us to the end of question 18. Let's continue to question 19. Question 19, this question is about benzene, a colorless liquid first isolated in 1825, and some related compounds. They say 3 carbon 6 hydrogen 6 structures proposed in 1860s in the 1860s are shown. So there was the Kekulé structure. I think everybody knows about this. There was the Dewar structure and then the Loddenberg structure. So we had three structures. Again, I can try to cut out this so that you can see the structures initially, then I'll return those. So here we can see this one here is the Loddenberg structure. It's still carbon 6, hydrogen 6. However, there is no carbon-carbon double bond shown. Here, of course, this is the benzene structure. Everybody knows about benzene and about the Kekulé structure. However, the Dewar and the Loddenberg are not that commonly talked about in the A-level textbook, basically. So they say that, let me take this back. Okay, let me bring this back. Okay. So they say the delocalized model for the structure of benzene has been accepted since the 1930s, following the study of its X-ray diffraction pattern and understanding of electron delocalization in bonding theory. The Dewar and Loddenberg structures have since been isolated as stable compounds, but there is no compound with a Kekulé structure. So we can say that it's kind of theoretical. A says, describe a chemical test including the results that could distinguish the Dewar structure from benzene. So we're going to look at the Dewar structure and benzene. As you can see, in benzene there is delocalization. Actually, the carbon-carbon double bonds they're not similar to the alkyl carbon-carbon double bonds. So in this case, we expect the Dewar structure to give a positive test with bromine water, while benzene will not give a positive test. So that is the only way we can distinguish the two based on the carbon-carbon double bond. So I said use bromine water, or you can say aqueous bromine. The Dewar will decolorize bromine water, but benzene will not. So this part in green, you can say that as well, talking about potassium manganate 7 in acidified conditions, and then with the Dewar structure, we expect it to turn from purple to colorless, and with benzene it will not. However, the part in blue is the best answer you could write. However, this is also acceptable. The next part says, state one similarity and one difference you would expect in the low resolution proton NMR spectrum of the Loddenberg structure and benzene. Low resolution proton NMR, we have to look at the environments. How many environments do they have? You can see that in benzene everything is the same. They're all identical. So we expect to have one proton environment. So in the low resolution NMR there will be just one peak. Let us look here. 1, 2, 3, 4, 5. Everything looks the same. So since here we are looking at the similarities and the differences, so the similarities are both compounds will have one NMR peak due to each having one proton environment, as you can see. Now we could look at the chemical shifts. If you look at the chemical shifts, you'll see that benzene, the chemical shifts are going to be in the range of 6.4 to 8.4 ppm. Again, to get this answer, you have to refer to your data booklet, because they said you must refer to your data booklet to support your answer. If you look in the data booklet, there will be an area where you have a place where the peaks for benzene basically, or arenes, are going to be. So in this range, and the chemical shift or in Loddenberg structure will be in that range, because of course it's just alkyl. There is no carbon-carbon double bond also, so it will just be HCC from the data booklet. So I will continue to the next part. Part C, explain how X-ray diffraction shows that benzene has a delocalized structure and not a Kekulé structure. Now you remember X-ray diffraction is going to be checking about the bond length of the bond, and since in the Kekulé structure we expect that the carbon-carbon double bonds are not movable, they are in one restricted position, it means the carbon-carbon double bonds are going to be shorter than the carbon-carbon single bonds, so we would expect that kind of data to be visible in the X-ray diffraction. However, so let's see here, I say X-ray diffraction data shows that all carbon-carbon bonds in benzene have the same length. In benzene, because there is delocalization, the carbon-carbon double bonds are not restricted in one position, but it's like there is a flip-flop all over. It means all the bonds are going to have the same length in benzene, while in the other structure, in the Kekulé structure, we would expect the carbon-carbon double bonds to be shorter than the carbon-carbon single bond. So that is the only difference between the two. Okay, the next question says, the Loddenberg structure and Loddenberg and Dewar structures both isomerize to benzene, meaning they can be converted to benzene. The enthalpy changes are negative 376 kilojoules per mole and negative 297 kilojoules per mole respectively. So this is for the Dewar and that is for the Loddenberg. So they said draw a Laborde enthalpy level diagram showing the relative thermodynamic stability of the Loddenberg structure, the Dewar structure, and benzene. They want you to include the enthalpy change values in kilojoules per mole. So let's see. I began by drawing, you can see the Loddenberg structure up here. Remember they've told us it is, for Loddenberg is negative 376 kilojoules per mole, and that's why you can see this long one. And again, I want you to see that. It means to convert it to benzene, you will, that is the enthalpy change, so negative 376 kilojoules per mole. However, to convert the Dewar to benzene, we need negative 297 kilojoules, which is that. And then we needed to find the enthalpy change required to convert the Loddenberg into the Dewar, and that is that. Remember, the question is asking here, include the enthalpy change values in kilojoules per mole. They want us to basically show everything. So here I showed to convert the Loddenberg into the Dewar. The difference between that and that is negative 79 kilojoules per mole. And that is how you would represent this part. So I will continue on. Here they say, give a possible reason why the isomerization of the Dewar structure to benzene has a lower activation energy than the Loddenberg structure to benzene. So here we need to think about that the Dewar has pi bonds, and these they're going to be weaker, so they will require less energy to be broken in comparison. So the Dewar structure has pi bonds, and these are weaker, and therefore they will require less energy to be broken. So you're breaking the double bonds to convert it into a single bond. The energy required is going to be less in comparison to the other part. So the next question says, the enthalpy change of hydrogenation of hex 3-in is negative 118 kilojoules per mole. They've given us the equation here. And then they say the table shows the enthalpy changes of hydrogenation of 2 further alkenes containing 6 carbon atoms. So there is the E-hexa-1,4-diene and the E-hexa-1,3-diene with their respective enthalpy changes of hydrogenation. So then they say, use your knowledge of benzene thermochemistry to suggest explanations for both of these enthalpy changes of hydrogenation in relation to the value of hex 3-in. So we have to look at it respectively. I want to take you back again to look at this data here. They've given us this is negative 118. Remember, this is one carbon-carbon double bond. It requires negative 118. So I would expect that for 2 carbon-carbon double bonds, it's going to be twice that. And then this should also be twice that. However, we can see, since this has 2 carbon-carbon double bonds and that has 2 carbon-carbon double bonds, you would expect that their enthalpy changes of hydration are going to be identical, which would be actually twice the energy, the enthalpy change required to convert 1 carbon-carbon double bond into a saturated compound, basically. So here I say, in E-hexa-1,4-diene, the enthalpy change is twice that of hex 3, which is negative 236, which is twice basically negative 118. So we can see this makes sense because it's twice this for 2 is twice that for 1. However, there is a problem here. The reason is these carbon-carbon double bonds are so close and there is delocalization. That delocalization makes this structure more stable and therefore the enthalpy is going to be lower than predicted. So here I said in E-hexa-1,3-diene, the enthalpy change is less exothermic. That would be that. So this is not twice that, and the double bonds are close. Some delocalization happens. Yes, the double bonds being closer, some delocalization happens, and this will make the structure more stable by 22 kilojoules. How do I know? You have to get this value minus that. It's going to be about 22 kilojoules per mole. So I will continue to the next part. Methylbenzene. Here we have methylbenzene. They've given us the formula. Reacts with ethanol chloride. This is ethanol chloride in the presence of a catalyst aluminium chloride to form a mixture of organic products with the formula that. So let's see. This is the reaction they've given us. Okay, let's continue. They said draw the skeletal formulae of 3 different arenes with the formula that. Now, if we are drawing, we need to know that this carbon-6 hydrogen 4, basically this is the ring, and this other thing is just connected to the ring. So we have to begin by positioning. Since this reaction is introducing this CH3CO as the electrophile attacking the ring, and it's already methyl benzene. Methyl benzene will be like that. If methyl benzene reacts with ethanol chloride, it means ethanol chloride is going to come like that. That is the electrophile. Since there is a methyl group here, the methyl group is electron donating, and therefore it is going to cause substitution reactions to kind of occur more easily. And if they occur, it could occur on position 2. It could be on position 2, so we have a 1-2 position, or it could occur on position 3, which would be the same as if it occurred on position 5. I'm taking one at a time, and it could occur on position 4. So it can be position 6 or 2, which is the same, position 3 or 5, which is the same, or position 6. So let me erase that and show you the structures I have here. That is why I put this. The methyl benzene is that. This is the electrophile that has come in. It can be on position 2. If it's on position 2 or position 6, the structure will be exactly the same. So 1,2 is the same as 1,6. The next part is if it's on position 4, there is no other way. So 1,4 is just, yeah, that's it. And then if it's on position 3, it's the same as being on position 5. So that is still the same structure. So these are the 3 possible structures I've shown here. And then I can go to the next part. The next part says the carbon-13 Nmr spectrum of one of these arranged compounds, X, is shown. So they ask, identify compound X, use the number of peaks on the carbon-13 NMR to justify your answer. I want to go back up here. We're going to count the peaks, and then we'll refer to the 3 structures we have here to predict which one is correct. So we have the first peak, the second peak, the third peak. Here they've told us there are 2 peaks, so it will be 1, 2, 3, 4, 5, 6, 7. Since we have 7 peaks, it means we have 7 carbon-13 NMRs. Remember, this is a carbon-13 NMR, so we need to look at all these 3 structures and determine which one has only 7 proton environments. I will begin with this one. It has environment 1, the methyl part, the environment 2, 3, 4, 5, 6, 7, 8, 9. All the carbons are unique, so it has 9 carbon-13 environments, and that is not the answer. I will come to this. It has 1, it has 2, that and that are identical, so let me call those 3. That and that are identical, I'm going to call them 4. This is unique, 5. That is unique, 6. And that is unique, 7. Oh, 1, 4 fits whatever we're looking for. However, let me first look at the other part. It has 1 carbon, the second environment, third, fourth, fifth, sixth, 7th, 8th, 9th. So 1, 2, and 1, 3 have 9 carbon-13 environments, while 1, 4 has 7 carbon-13 environments, meaning the structure we are looking for is this structure as you see here. And I drew to show you all the environments. 1, 2, 3, 4, 5, 6, 7. So this is the isomer we are looking for. Let me continue to complete the diagram, including curly arrows to show the mechanism for the formation of compound X in this reaction. They say include an equation for the regeneration of the catalyst. So here they've given us the equation for the formation of the electrophile. Again, this is ethanol chloride reacting with a halogen carrier or the catalyst, producing the electrophile. So this electrophile is going to receive electrons from the ring, as we can see here. So in the first step of the mechanism, and again before, remember ethanol chloride is that. However, when it's converted into an electrophile, that electrophile is going to be presented like this. Or you could present it like that. As we can see, it was presented in this part of the book, so you put a positive there. So they used this symbol to symbolize the electrophile. I'm going to go with that. So the first step is for the ring to donate basically a pair of electrons to the positive carbon in the electrophile. And then we can see then the ring opens up. Remember, this opening is facing the side where the electrophile has attached onto, and the hydrogen on that part is going to be exposed out. That is the first step. Then in the second step, it's usually advisable for you to show this intermediate and not work with this, but bring it down here, and then the next step is shown on here. Because if you make a mistake, if you show it from here and you make a mistake, then you could lose marks. So I always tell students, put it here, and then do the same thing down here and do the steps that follow after that. So here, this carbon-hydrogen bond breaks, returning the pair of electrons in the ring, and then, of course, the hydrogen is going to break off as H+. So here we have created the 1,4 isomer. However, in the final step, remember they have told you to include the equation for the regeneration of the catalyst. So the other product here, this one here, is going to react with the H+ created to produce HCl and AlCl3. That is the catalyst regenerated. This is the end of question 19. Question 20. This question is about titanium 3 chloride. Titanium 3 chloride is used as a catalyst in the production of polypropylene. State the property of transition metals, such as titanium, that makes their compounds effective catalysts. Transition metals they have variable oxidation states, and due to that, they can easily be oxidized to higher oxidation states and then be reduced back to their original state. So that ability enables them to act as catalysts in any reaction that they could be used. Part B says, when dissolved in tetrahydrofuran, here we have that, so it's a titanium, 3 chloride forms a blue solution containing complex Y. So let's see, this is the tetrahydrofuran, or what you call THF, and this is complex Y. We see it here. So the first question here says, THF acts as a monodentate ligand in compound Y. Remember, this is the ligand they're talking about. If it's monodentate, it has a lone pair on oxygen. It uses that lone pair to form a dative covalent bond onto the central metal, which is titanium 3+. So they say, state the meaning of the term monodentate and ligand. These are two terms. I said monodentate refers to monodentate because it forms a single lone pair dative covalent bond. That's it. And then a ligand is a species with a lone pair that forms a dative covalent bond to a central transition metal ion in this case. So this is a ligand, but because it attaches with one dative covalent bond, we can call it monodentate. So I will go to the next part. Here they say complex Z is a stereoisomer of complex Y. So complete the diagram to show the arrangement of the ligands in complex Z. So because complex Z is a stereoisomer, so it's basically arranging the ligands around the central metal ion in different ways, again in an octahedral shape. Since this is a stereoisomer, we have to make sure that the arrangement is going to be following the complement of part of the previous structure. So for me, I position this one here, that one there, and that one there in the complex Z to be able to agree with the stereoisomerism they're asking you to show actually. So let me go to the next part. A student determines the change in oxidation number of nitrogen when a solution of magnesium nitrate is titrated with aqueous titanium 3 chloride. So this is a 3-step procedure. Step 1, using a volumetric flask, prepare 100 centimeters cubed of an aqueous solution containing 0.750 grams of solid magnesium nitrate. This is hydrated magnesium nitrate. Then step 2 says, pipette 10 centimeters cubed of the solution from step 1 into a conical flask and add a few drops of alizarin indicator. Then we add 2 centimeters cubed of concentrated hydrochloric acid and heat the mixture. Step 3, fill a burette with 0.0850 mole per decimeter cubed aqueous titanium 3 chloride and titrate the contents of the conical flask from step 2 while continuing to heat the mixture. So here they say, during the titration, titanium 3+ ions are oxidized to titanium 4 ions. This is the equation we can see here. So they say alizarin indicator is green in the presence of titanium 3+ and yellow in the presence of aqueous titanium. So this is titanium 4. The endpoint of the titration is reached in addition of 20.7 centimeters cubed of aqueous titanium 3 chloride. They state the color change that would be observed at the end of the titration. Now, when we titrate, remember the 3 from the burette, I will say that, is going to be converted to that in the conical flask. So it means as this is released into the conical flask, we're going to have a conical flask color change based on the titanium 4 present. So since they've told us it's going to be yellow in the presence of titanium 4, it means the color change at the end point is going to be from yellow. That is going to be the color of the solution, since the conical flask is going to have a lot of titanium 4 towards the end of the titration. So it's going to be looking yellow. Then they told us alizarin green is alizarin indicator is green in the presence of titanium 3+. Since you are releasing titanium 3+ from the burette, at the end of the titration, a drop of titanium 3 is going to be released in the yellow solution containing a lot of these. And since the indicator is going to be yellow in that, when you add the extra drop of this, it is going to cause a permanent pale green color to occur, since this is going to be green in the presence of titanium 3+. So I don't want to say green, but we say pale green because there is going to be a dilution in the solution. So that is why I say yellow to permanent pale green. So let me continue to the next page. Here they say, use the results to determine the fine oxidation state of nitrogen in the titration. You must show you're working clearly. Here they've given us the MR of this whole thing as 256.3. So I will begin. Since we have the information concerning titanium 3, we have the concentration and we have the volume. The concentration is that. The volume is that, but divide by 1000, you convert the volume to decimeters cubed. So we can find number of moles as concentration times volume, giving us the moles of titanium 3. And now we can find the moles of the hydrated salt. Since we have the mass and we have the molar mass, we can find the number of moles in 100 centimeters cubed solution of the hydrated salt. We also need to remember that each mole of hydrated magnesium nitrate contains twice nitrate. You can see it here. It's 2 times, twice. Each mole, 1 mole, this whole thing 1, contains 2 of that. So it will contain 2 moles of nitrate in 100 centimeters cubed. Then we can use this to find moles of nitrate are going to be 2 times the moles of the magnesium nitrate. So since we got these are the moles of magnesium nitrate, multiply them by 2 in order to get the moles of the nitrate. So that is going to be the moles of nitrate. And now, since moles of nitrate, they react in 10 centimeters cubed. Remember, from the 100, they transfer 10 into the conical flask. So we have to find the number of moles of nitrate that reacted in the 10. And this is going to be divided by 10. 100 divided by 10 gives you what was present in the 10. And this is going to be that. Remember, this is present in 100. Okay? And when you divide by 10, you get those present in the 10. So these are the moles. Now, to find the mole ratio of titanium 3 to nitrate, we'll go back to the moles of titanium 3 and the moles of nitrate we've got here, get the ratio of that to that, which gives us 3 to 1. So we can say that 3 moles of titanium 3 plus reacted with 1 mole of nitrate, and therefore, since each titanium 3 will lose 1 electron to become titanium 4 during oxidation, it means we will basically need 1 mole of nitrate is going to gain 3 electrons. So the ratio should be, as you can see here, this is coming from 5 oxidation state, and then we can see it's going to +2, 3 electrons are going to be gained. Yet this titanium uses up titanium to go to titanium 4 being oxidized. It is going to lose 1 electron, so we will need 3 of these, and then the other is going to be 1. Therefore, the final oxidation state of nitrogen is going to be 3. Again, to remind you, if titanium 3 is losing, titanium 3 plus is going to titanium 4. Let me use a 4 plus. I'm not going to put the oxygen. Let me just do like that. And we have seen that the ratio of that to nitrate as they react, this is going to be 3, and that is going to be 1. It means, since this is 1 per 3, it means this first reaction produces 3 electrons to produce that. It means these 3 electrons have to be used up by these in order for that redox reaction to be completed. And since this is in 5 plus oxidation state, receiving 3 electrons takes it to 2 plus oxidation state. That is why I say the final oxidation state is going to be +2. Let's continue to the next part. Write the overall equation, ionic equation for the titration reaction using your answer to C2 and the relevant half equations from the list below. So remember, we are looking at titanium 3 being converted to titanium 4 and nitrate being converted to into plus 2 oxidation state. So it means, as you can see here, I labeled them. Here we have a 4 plus and a 3 plus, and here we have a 5 plus and a 2 plus. So we're going to use that equation and that equation. Now, when we look at their potentials, we can see this one here is less than that. Anyway, even if you don't look at the potentials, we have to follow the reaction. To be able to oxidize titanium 3, it means this equation is going to be reversed in that direction, and this is going to go as it is here, meaning 3 of these are going to generate 3 electrons, and those 3 electrons are going to be used up by that to give you that. So I changed this equation, as you can see, and I rewrote it, putting this one and the water as the first part, and then that on the other side, and then I wrote this as it was, you can see here. Now, because this one has been reversed, it's going to be on the left, and this will be on the right because it's gaining electrons. Remember, the half cell on the left is the one that gets oxidized, losing electrons, and the one on the right gains those electrons. So to combine the two equations, I had to make sure the electrons are the same. Since we have 3 electrons here, I have to make sure I multiply the whole equation by 3 to ensure that the electrons are exactly the same before I combine the two equations. And combining the two, I get this. Add up that to that, to that, to that, and then that to that, to that, to that, cancelling out to that as well, cancelling out anything that are similar. You can see on this side we have 2 water molecules, and here we have 1, so it means that is going to cancel out, and we just have 1 more water molecule on this side. And we have 4 hydrogens here, and here 6 hydrogens. It means this will cancel out, and we have just 2 hydrogens on the other side. So you add up everything and cancel out things that are similar on both sides, then you get what remains. So the next part says, use the electrode potential data provided to calculate the E theta for the cell for the overall titration. I say the E theta for the cell should be the E right minus E left. This is the E theta for the right half cell, and that is for the left half cell. Remember, I've said this is going to be on the left, and that is going to be on the right. So it will be 0.96 minus 0.1, giving us a positive 0.86 volts. You can see you have to put the sign and you have to put the units together for mark. And here they suggest the content of the conical flask. Suggest why the contents of the conical flask are heated. Every time you're heating, you're trying to speed up the reaction or increase the rate of reaction so that the reacting molecules have enough kinetic energy in order for collisions to occur successfully so that the rate can be increased. So this is to speed up the rate of reaction. Let me go to the next part. It says, the student's teacher said, as titanium chloride is blue and titanium 4 ions are colorless in the aqueous solution, the titration can be carried out without an alizarin indicator. Because, of course, there are these colors already, so you can know if it turns from blue to colorless. We can confirm that the titration is over. They say, assess the teacher's statement. In your answer, you should identify by name or formula a colored complex ion expected to be present when titanium 3 chloride dissolves in water. You need to explain how the color of this complex ion arises and suggest why the titration may be more accurate with alizarin indicator. So I first talked about the complex. I said when titanium 3 dissolves in water, this complex is going to form. Remember, the chloride separates from the titanium 3 plus, and then this is going to gain water ligands around it, forming a hexa-aqua complex. And then these ligands, as they approach it, they're going to split the d orbitals. So here I said as the ligands approach the center metal ion, they split the d orbitals into different energy levels. You guys remember ligands split the orbitals, creating 2 sets of 3d orbitals, those with lower energy and those with high energy. And then electrons are going to transition if the energy is available to transition electrons. So that transition requires energy, which is got from the light or wavelength around them, and that's how color originates due to the unabsorbed light. So here I say, since titanium 3 has partially filled d orbitals, it allows for electron transition. Because it has partially filled d orbitals, there is going to be some space for electrons to transition from the lower d orbitals to the higher d orbitals, and when a photon of light radiates on the sample, some of the light is going to be absorbed by the electrons and that energy will be enough for the electrons to transition to the higher energy levels. Then the unabsorbed light has a wavelength corresponding to a specific color. Remember, the color you see, the color of the complex you see is due to the unabsorbed wavelength or unabsorbed light, or it could be, somebody can say, transmitted or something like that. So the unabsorbed light has wavelength corresponding to a color in the visible region. This is the color observed from the complex. And finally, the titration may be more accurate. Now here, this is in response to the titration. Why use the indicator? The titration may be more accurate if the indicator is used because it's going to be clearer. You'll be able to see a clearer color change or endpoint change when you use an indicator instead of not using one. Or if you do not use the indicator, the other colors could be harder to tell apart. But when you use an indicator, it's going to be easier for you to tell apart the colors. So this brings us to the end of section B. Again, thank you for being with us and thank you for watching our videos. Please do remember to subscribe, and do not forget, I put the links to the two videos, section A video and the section C video, in the description box. You can check them out. Thank you. See you next time.